originally had planned for these one series. We had a bit of a hiccup in the lockdown, but we got through it and we're back on track. So again, the whole ROS series workshop is coming together as part of a collaboration we're doing with Robotics Club as well as Electrical Engineering Student Society, or EESS. And we're basically bringing these workshops together to prepare you in your engineering career. So basically, we did the circuitry PCB workshops last sem. We're doing ROS workshop this sem. Along at the same time, EESS is running the Raspberry Pi 101 workshops. So basically going into the depth of what a Pi is and why you might want to be using it for your projects. We'll be using most of it today as well. So I've got Pi kits here in front of you, as well as servos, some jumper leads, and thanks to robotics, we also have some sensors available that will be interfacing with that I'll show you today. Okay. So today's plan, as we had said earlier, would be hardware integration. But before we get into it, I might bring Ryan to talk about some of the projects that Ryan's doing in robotics, and I will talk about EESS tonight as well. Okay. Oh, yeah, sure.
Okay, so on the Robotics Club, we have a few projects going on at the moment. Some of you guys already got our members. So our main one that we're slowly working through is RoboDog. Got Boston Dynamics Prop Mini. Guy called James Bruton, an English engineering YouTuber, created a mini dog, a open dog version. And so we're basing our design off that and making it custom and a bit easier for us. So that one's going to be a long-term project for our mini dogs, where we've taken a design online, bringing it up to us, and there's going to be a software development platform for us to use later on in RoboDog once that gets up and running. We've also spared all of the you guys are learning and you're taking this on yourselves and you're doing the design work. Then we've got our ones where we're helping you along the way. We're doing this with you, which is the case cam. So we're attaching a Pi camera on a pencil so it's to an RC car, and that's going to be used to use computer vision to track objects whilst you drag the car around. We've got Armageddon. That is a mobile. It's going to be a mobile platform using Omni wheels. If we can get a couple of them fixed up, they're possibly going to be used for the ROS workshops once we get onto robot movement and control. And then as a bit of a side project for those who are more interested in IT, we've got a Pi cluster that we're wanting to try and develop. So for us to do computation work, hosting Discord bots and the like, also thinking it might be useful for remote ROS workstations. So those are a couple of things that we're doing. Certain projects, we have our little workshop, you're learning things, collaborating with Aerospace and EESS to bring you some of those, and the general industry events that we try and bring to you guys so that you can get a feel of what else is out there in the industry.
Thanks, Ryan. Unfortunately, Daniel or Margot are not here from EESS tonight. They couldn't be here. I'll just report from them as well. So they do most of the electrical engineering workshops, so things like PCB designs, looking after your Pis, your Arduinos, your TNT circuits. How do you take a circuit like a TNT or a flashing circuit that you might have done in 120, and how do you turn that into an actual embedded circuit or a PCB? How do you take it from a circuit design on ThinkerCAD and get an entire PCB, solder it together so you've got it ready to go for your custom projects? Okay. And for aerospace, we've been doing rockets, ROS, and drones. We've got lots of platforms on here that we've been working on. And the biggest one that you might have seen last year, which was like your Summons, still is here if you want to work on it. We've also got other fixed-wing aircraft like gliders and growlers, if you want to work on those to start them, getting them up in the air. We've also got rockets. So last week we had our rocket workshops, and we've got 3 rockets ready to pretty much in the build, ready to go. Almost, yeah. And yeah, and if you want to do more rockets, we'll be putting more workshops on the entire semester to do our September launch. If lockdown doesn't move. Yeah. So our next big event that I want to sort of talk about is AirCon. So AirCon is coming up next week. It's the big industry event that all the 3 clubs are coming together for. It's going to be online this year because of the space restrictions with COVID, but it's on Gather Town. We're going from 12 p.m. to 5 p.m. It's a big 5-hour session. Drop in any time. We'll be having multiple industries. We'll have Q&A sessions. Gather Town is kind of like an online conference style event. So you just walk in and you can go up to any industry tent or stalls, or you can join the Q&A group or the theaters where they'll be presenting about their companies, like a normal virtual conference. Yeah, so tickets are out. They'll be on all of our events. It's actually free for students, so we'll be taking all the costs for you. You just have to sign up through the Eventbrite link and rock up on the day. So any time for the day should be fine. Come on through. Yeah, keep an eye out. There's going to be follow-ups to the Aircon event in the future. So yeah. Whoop. That went right to the end. Cool. So we're into this Series 2 workshop right here, which is mainly focused on drivers and hardware. So obviously, there's lots of types of hardware, lots of types of drivers, and it's almost impossible for me to cover everything. So what we're going to be looking for today is how do you pick what you want, and how do you go about looking for its drivers and ROS? How do you go about thinking about interfacing it with something like Raspberry Pi? Or if you're working with an Arduino board, then how do you go about doing it on an Arduino? Or if you want to go a bit more microprocessor style, then TNCs or your Atmega 32 boards and things like that. So we'll look at how you can match the architectures, how do you match the GPIO pins, and how do you get the input-output from each other. And then next week, we'll be doing some computer vision and some rudimentary control. Not going to go into some in-depth control, just simple vision-based control. And then finally, the advanced concepts workshop. We're thinking of bringing the Armageddon arms from robotics to show you how you can put everything together, have a camera and component, have a robot based on that. Okay. So last year in the workshop one, I introduced you guys ROS, and I talked about all these platforms, one of them being the Raspberry Pis and Arduinos that I've been mentioning all day. And we have got those right here. You've got all the Pis that you might need for today, as well as some servers, we've got jumper leads, and some sensors. I've also got TNC 0 if someone's keen on doing some C programming more than Python. Word of caution, it is very low on RAM, so you're going to be programming very tightly. Yeah, so hardware integration, we're going to be looking at basically what makes an autonomous system. So to make an autonomous system, you kind of need these 4 main systems to work together. You need to know state estimation, which is basically where you are in the world. Based on that, you need to do control, where you want to go. And then once you've done that, you need to understand how the environment's moving around you, which is mapping. And then based on how the environment's moving, you need to plan ahead. So do things like obstacle avoidance or planning a waypoint map and things like that. Obviously, we're not going to be covering each of those systems very much in depth. There's a lot of units at QUT that deep dive into all of these sections. The state estimation is done really well with 339 and 439, robotics and advanced robotics. Controls done by 345, 445, 446. Control dynamic systems, body control, autonomous systems, I think they're called, as well as 450, which does a lot of robot-based control, which is the advanced honors unit for aerospace. For mapping, again, advanced robotics does mapping as well, based on EKS SLAM. If you're interested more in what this is in the background, which is understanding the world's behaviors based on that, have a look at those units. And planning's kind of covered between 445, 446, and 439. So these are mostly your 4th year units, which is your advanced robotics, modern control, and autonomous systems, which look at how you should be planning. Essentially what it is you've got your robot, which knows where it is, hopefully. And then you basically pick a point, which is going to be your goal point. So in this case, if I was to go to that tablet over there, I would know where I am with respect to the tablet. And then I would start looking at how I should move my current state, the state you're estimating, to get to the goal point, which in this case would be go forward, and then keep adjusting the heading until I'm at the tablet. Things like that. So the key important state for anything is going to be state estimation. Before you do any sort of planning, you need to know where you are with respect to everything in the world. And some of the very common ways you can solve the state estimation problem is if you're outside, you can use GPS. If you're in a GPS denied environments, you can go over to IMUs or motion capture sensors. So things like this in the bottom right corner, where you've basically got your robot and it has a bunch of reflective surfaces that an array of cameras track, and they give you a real-time positioning system of where you might be in a 3D space. The way IMUs work is they've got an inbuilt sensors that track a lot of your forces on the aircraft, or the platform, I should say. And then you can use a bunch of fancy physics and math equations to try and figure out where you might be in the world. And then GPS, it's just a global positioning system which uses the satellites around the world in space that triangulate your position on the floor. So GPS works great for outdoors, and it has an accuracy of about plus or minus 3 meters. You can get it down to 1 meter depending on how well your GPS sensor is. You can also pair them with an RTK setup, which is called the real-time kinematic setup, which does real-time computing along with the GPS module. It's kind of like combining IMU and GPS together to get you a better understanding of where you might be. And then motion capture setups, they're really expensive. They're kind of limited to whatever space you're working with. So if you set it up in this space, you can't really go out of S901 anymore. You're kind of restricted to that space. If you ever want to do anything outside of a confined space, your 2 major options are the top 2. And also there's other ways of doing other things. So you can do gyroscopes, you can do magnetometers, ultrasonic sensors. It's kind of just combining all the data together to bring it all together. And the technique that combines it all together is known as sensor fusion. So which basically takes a bunch of data from different sensors and makes them sense out of it. So today we're going to be focusing on state estimation based on IMU sensors, specifically MPU sensors. So what an MPU sensor really is it's a mix of multiple sensors, and it stands for Measurement Production Unit, I think, something like that. Essentially, it's got 3 main units that it actually has. It's got an accelerometer, which looks at your acceleration in linear space using an IMU sensor, which is inertial measurement units. It has a gyroscope, which looks at the rotational velocity of your platform, so essentially how quickly it's rotating. As a result, it gives you rotational velocity on all 3 axes. And then you've got a magnetometer, which gives you reference heading to true north. Magnetometers are kind of really tricky with these sensors because when you're working with robots, you've got motors, current, batteries, and they all have magnetic interferences. So quite often you'll see magnetometers being put well away from everything, shielded in like aluminum foils or cardboard aluminum boxes, which try and avoid these interferences for it. Cool. So very quick and easy way of doing state estimation is the dead reckoning way, which is basically you take your measurements, which is your linear accelerations, and if you do any sort of math or physics, you know you can double integrate it and get your position, which is the state you're at currently. And that comes with a very heavy cost. So if you use a noisy sensor and you know how integration works, noises get integrated and they actually add up very quickly. So you can look at adding filters and things like that, which is what a lot of the units will do at uni, and they'll ask you to do at uni as well. We won't go too much into depth of that, mainly because ROS already comes with a nice package that does a lot of it for you. And so we'll be relying on that pretty heavily today. Okay, so some of the tools I want to introduce to you guys today is RViz. So the ROS package we installed last week, we installed the full ROS package, or the full desktop ROS packages. And it comes with a lot of built-in tools that you quite often will see being used in the industry. So what RViz is a 3D visualization tool. It basically subscribes to your ROS master. So if you go back to workshop 1 that we had, ROS master being the person, the main node that looks after what's going to be happening on your platform. It looks after that, and essentially what we'll do is, give me a second. I'm just firing on my Ubuntu system, sorry. So what it will do is it will subscribe to your topics, and depending on your messages, so right at the end of the workshop 1, we looked at what ROS messages are. Essentially, they're a way of structuring how data is going to be exchanged between 2 parties. It's kind of like a way of communicating between 2 nodes. So it looks at those messages and where the data is coming from. It subscribes to those nodes, and it will actually look at publishing that data out to you. So if you're using a lot of the standard packages, you will actually see a lot of the data pretty much ready to go from ground up. So if I bring up my Ubuntu machine, I should be able to show it to everyone on what I mean. Very tiny. Oh, wow. It doesn't want to play. Can you see that screen on Zoom, Jess? Cool. Okay. The resolution isn't the best on the projector, so bear with me while I try and get this up and running. So what we'll first need is we'll get our ROS core to bring up our ROS master on a local server, and then we'll just bring up RViz for now. So RViz is an inbuilt tool. What it allows you to do is it essentially allows you to look at a lot of the information going around on this platform. So there we go. The resolution is not the best. Okay, so what basically will happen is you will see all your topics and a lot of the messages you're publishing on this side of the platform. So on the left panel, you will see everything that gets published around. And you can very easily add more topics. So if you go down here, you'll be able to see the add button at the bottom. And once you click add, there will be a pop-up that allows you to pick what you want. So you'll see all these standard messages that ROS comes with. Axes, so if you've done any sort of transfer functions or you know how coordinate axes work, you can put them up here to try and locate where things are with respect to each other. You can get your camera input, so if you've got a Raspberry Pi camera or a webcam or a separate camera, you can put that in through as well. A depth cloud camera, so if you look at things like the RealSense cameras, the D455 series or D345 series, the one that Robotics Club is using on the Robodogs, you can get the depth sensing images directly onto ROS as well. And then you can start overlaying them with your camera image to get a colored depth map, which is quite cool to know because that makes navigation a lot easier. Then you've got efforts, fluid points. These are more for specific sensors. Some of the other ones you'll use quite often is things like laser scans. So these are more for your LiDARs. So if you've seen LiDARs, basically a sensor that shoots out a laser in 360 degrees, and then it reads the readings of those. So laser scan just puts that on a map. So if you pair up a laser scan with an axis, you can basically tell where your LiDAR is in the 3D space, essentially. And then you've got your odometry, path planning, point cloud, which are a lot more advanced, and these are more getting into that second part of the autonomous systems where you start mapping and planning around. So you can very easily add a lot of these topics. All you literally have to do is go and click the topic you want. So let's just pretend that we've got a topic of camera for now. And obviously we don't have a camera connected to my computer currently, but if you did have a camera that was publishing on a camera node, you should be able to go into that node. So now that we have added a camera layer, we should be able to open that layer and just set the topic to that topic we have the camera publishing. Then you should be able to see all the images that are coming out of your ROS packages. This is kind of the beauty of ROS, because now you can have camera running on C to try and get you as many frames per second as you want. But then you can have your big ML models running in Python, and it will be able to do your odometry and a path pose all in the RViz platform. So everything can still interface in different languages. The other really cool thing that I learned when I was at Saro was you don't even have to do this specific thing. If you've been using the direct standards that ROS comes with, and you've been using the standard messages that ROS comes with, you should be able to go add and then go add by topic at the top right. So right there. And it will automatically pick up the topics you're publishing, and it will pick up what messages you're publishing, and it will automatically give you options to put that directly on a map. So this was from one of the projects I was doing where I had a goal pose, which is same as saying that the tablet is with respect to me. It will put out an arrow saying you need to head this way. And it shows you how the robot's thinking when it's out in the real world. where you can't have a screen or no one's on the actual robot. Okay, so Alva is a really good platform for visualizing a lot of things. It's actually really powerful, and once you start knowing how to use it properly, you'll really appreciate the skills that it comes with and the beauty of having different nodes working together. The other really big one that you'll use quite often is RQT plot. So if I close this very quickly, the other one you'll use quite often is RQT plot. And it's underscore plot. RQT plot. Okay, give me 1 second. I'm pretty sure it's RQT underscore plot. Yeah. Yeah, that works too, actually. Yeah. So RQT is the main utility that provides a lot of these tools, which allows you to render it as well. There we go. And so RQT's got RQT plot, which is what I was trying to say earlier. So if you've got data points that are outputting plots for things like IMU sensors or altitude meters or height sensors, barometers, the PO2, to your velocity, things like that, you can put it on a plot over time series data, and you can see how things are tracking along time. So let's say, for example, if you've got a ground robot and you're estimating X and Y positions, and you've ordered your robot to go forward, you'd be expecting your X position to be changing, but not your Y or your Z position. And so you can see it in the real time, making sure that the code is actually reflecting what you expect in real time. So you can add a bunch of configurations. So the plot configuration is part of it, as well as service calls and method publishers. So as well as visualization. So there's the RViz, which is what we were showing earlier. There's also plot, which is just mainly plotting everything. Image viewer, if you just have a camera and you don't want to do the RViz, which is sometimes a bit more resource intensive, and just want to have a quick look at the image, you can do the RQT image viewer. That works as well. As well as TF, so transfer function frames and transfer function trees. So quite often, this is a project we're doing with robotics right now, where if you've got a robot, for example, which has a lot of sensors, a lot of arms and legs that move with respect to each other, you can put a transfer function for everything. And what ROS will realize is once you give it a transfer function saying, hey, I've got a camera on body frame, it will automatically figure out how that body frame should enact on a arm that's on the top right or top left, because it's got a tree of all the transfer functions to go from camera to body, then from body to the first leg, plus leg to the hip joint to the leg joint, and things like that. So this is what the TF tree allows you to do. It's known as transfer function tree, or basically the columnar transfer function that allows you to transfer between frames. And you can see all of this once you've already set it up. Currently, I don't have anything set up, but as we go along with the project, we'll be seeing a lot of these tools being used all around the place. And I just want to introduce these tools so that people can see it and know what to go for when they start developing. I've got a chat. So we'll sort out all the frames to give you a point in a global frame. What do you mean with that, Jordan, with respect to like transfer function? Yes. So if you give it a starting frame and a goal frame you want it to go to, it will automatically calculate the transfer between all the frames. Yeah. Yeah, it is pretty sick, which is why it's so cool, because once you've got a transfer tree ready, you can just add sensors and not have to worry about transferring how it reacts with the robot. Cool. Back to the PowerPoint. So we saw the ROS tool, so I might as well quickly explain it. So usually when you add something, you want to do it in the orders of 1, 2, and 3. So make sure you've added the topic up here, using the add button, change the topic so that it's listening to the right topic you're publishing to. Make sure you haven't got any errors. If you've got an image, you'll quite often see the images being rendered here. And then the third position is your three-dimensional space. You'll see all the things coming to life. So the next part we're going to go into is ROS packages. So last workshop, we actually created a custom package called the Chatterbox. And it had 2 nodes. We had a publisher node, which talked, and then a subscriber node that basically listened to what was said and added some more words to it. That's known as a package in ROS, essentially a bunch of scripts that represent some functionality for something. And there's already a whole open source community with ROS that everyone contributes to. So quite often you'll be able to find drivers, firmwares, things like packages, do a whole bunch of things, all ready to go. I've seen at hackathons where students come in with a ROS pre-installed, and they can get a robot path planning and mapping within 2 days. And that's the thing that used to take over 2 years for students to do and researchers to do out of research labs. That's what the ROS comes with power. It's the power of ROS and the packages of open source community. So one of the really common ones that you might see is, I'll bring it up here. ROS Global Mapper, Global Planner. This is a very openly available ROS package for basically global path planning. And it implements A-star, Depstar, D-star, and a whole bunch of different pathfinding algorithms ready to go for you for your packages. So you can see it supports kinetic, melodic, and noetic for ROS 1. If you're doing ROS 2, there'll be something very similar for ROS 2 as well. And it's basically got all the documentation here. So if you look at this right now, so if you've done any sort of robotics units, you might pick this up very quickly. This is known as an occupancy grid. Basically, it's a grid of where obstacles are and where you are. And then it starts planning a path around these obstacles so that it knows to avoid them. So in this case, this is like a top-down view of what the map looks like. And all the things in gray are obstacles that you want to avoid. And then this red zone is getting your proximity to these objects and walls. And then your yellow path is the path that it's using to get around the obstacles. So this is a very quick way of getting planning into your robot. And if you scroll down, you'll be able to see, so there's the A-star algorithm that's very famous for path planning, as well as Dextra, so another really popular path planning algorithm. There's a whole bunch of algorithms just predefined for you. And then there's orientation filters. So these basically look at how you want to get from A to B with a specific orientation heading. So if you've got a drone and you want to make sure your camera's facing in the right direction when you get to a goal position, because drones are pretty much a 6-degree freedom platform, you can get to the goal position in any orientation you want. But if you have a specific orientation goal you want, you can set those as well. And then at the bottom, it tells you what messages it publishes. So we can see that it publishes a nav message. Again, a very standard message, and we saw path thing up in ROS just a bit earlier. So that's the ROS path message that's pretty standard with ROS. It also takes in a bunch of parameters, so we can see which algorithm you want to run, what type of grid you want to see, and things like that. So there's already packages that people have made that are pretty much ready to go. And they're all open source. So you can download it, tinker with it, add more things to it, take things away, all up to you. It's under an MIT license, so you can't generally publish them under your name. But if it's under an Apture 2 license, you can even publish them under your name with modifications. And quite often, you'll be able to see those details at the bottom where they link the Git repo for you. So this one's under Attribution 3 Creative License. And yeah, if you want to know more about licenses, just look them up. There's many of them. So another really common one, so for example, for ours, we can look at the ROS package or ROS driver for an IMU sensor, right? Which is what we might be using for state orientation. And you can see there's already an IMU drivers section where someone's written that basically allows you to start writing drivers and interface with something. So it supports these IMUs, A lot of these you might already have seen, and it gives you a ROS API to work with, basically a node subscriber kind of style. And yeah, it uses the Robot Pose EKF package, which is just an extended Kalman filter package, which allows you to take out noise and discrepancies in your sensors. So this is the ROS Pose EKF. So there you go. So once you've got an IMU, you should be able to see your X, Y, and Z axis and how they deviate from each other. Okay, so a lot of cool stuff already out there. And this is why people love ROS. You can get up and running within hours, or you can develop your own custom package like we did last week and start tinkering directly on the board. Okay, so we'll go back to presentation. Cool, we talked about ROS, open source drivers. Okay, and then we'll be looking at hardware actuation today. So hardware actuation is basically, once you've understood something and reading the world around you, how do you make sure that you can control your robot? So let's say you've got a heading for an aircraft, you've got a roll angle. So I'll use my phone here as an example. Roll basically tells you how something is from your center axis there. So if you've got a roll angle this way, basically your platform's tilting in one direction. Or if the roll angle is in the other way, it's tilting the other way. So if you wanted to do something very simple, which basically corrects your roll, you can very easily have an IMU sensor, which looks at the rotational rate from your Z-axis. So if you've got a rotation across this side, you basically have an actuation server that puts it back forward. If you've got it that way, then put it back forward. It's a really simple node, subscribe and publish a node. You want to be publishing the orientation of your platform, and the subscriber would be your server node, which basically reads those in and applies a control input to correct it back to 0. So that's kind of what we'll be doing at today. Or we're looking at today. So we've got servos out here for you. We recommend a 9-gram servo for this, just because Pis don't output a lot of current. I think they kind of max out at about 0.5, 1 amp max, which is probably even not a lot of current you want to be pulling anyway. But 9-gram servos are pretty okay with it. Anything higher, do it at your own risk, and probably don't do it here either.
You definitely don't want to use the standard size servos running off the Pi. The current that the Pi is put out is for 305 lines, only got I think 300 milliamps, which is enough for 9 gram with like really nothing attached to it, like just like maybe for can-tilt servo stuff, just Pi can. Yeah. But anything else that's heavier, you will end up blowing like 33 volt rails by already. Because you just point too much current from it. Pretty much. Yeah, and I mean, if you want to control them, you can get current boosters or drivers. So you send a signal to the driver, and the driver looks after giving the right amount of current to the servos, which is what you do quite often with motors. So if you've done 320 or 450, you would have quite often seen a motor controller that fits in between the two as well, which allows you to make sure that that happens easily. We've got quite a few paths for Pis with normal ones that from normal servos. What's on our again at the moment, I believe they're using your the Pi and the chips on the boards. They can license the job to the servo. Yep, and that's quite often an easy setup to do. So what Ryan was explaining, which is just having 2 different platforms connected together. And in Workshop 1, I think we covered how you can have a ROS master running on main computer and still have something on a different platform talking to each other. Yeah. So we've got 9-gram servers here, and it's just the same system that I was explaining, which is we will do a simple yaw correction today, or roll correction today, which is basically, for now, just input a specific roll angle and see if your servo can actuate and correct it. And once you've got that working, pick up a sensor and then try and integrate it with the sensor so you can turn around and see if it actuates almost real time. Okay? Yeah, so the way you want to connect a servo with the Raspberry Pis, which we've got here, is you want to connect the red rail or the red wire with your 5-volt rails or 3.3 volts. We'll bring up the GPIO setup, GPIO pin layout in a second. And then you want to connect the brown on the black wire to your ground pin.
And then the yellow or the orange wire quite often you might see, which is your signal or your PWM pin. You want to connect that to one of your GPIO pins, which is PWM enabled. And that will give you access to controlling it.
And it's all kinds of wiring from these servers, red, orange, and yellow.
Yeah.
Red voltage, orange ground, and then yellow for your signal, which can be very confusing. But yeah, definitely see one has to go on short path to wire servers. Pretty much.
And yeah, so that's basically a lot of the content that I wanted to cover today. I already put together all the things you will need to start doing this on your Pis. So if you head on over to the ROS Workshop Git repository, you should be able to see all the things that you need for today. And that was posted in the Facebook event as well. So you've got that link there as well. If not, just look up ROS_workshops on GitHub and you should be able to find us there as well. So under README, you'll see ROS Workshop 2, which is being published, and it's basically covering what I covered in the content today. Just a very brief summary on what we're doing and why we're doing it, and the setup we'll be using. So I've linked the Ubuntu Raspbian image for the Raspberry Pis, along with ROS, which is already pre-installed, ready to go. And that's this link right here. If you just download that image and just flash it onto an SD card, grab a Pi. Pis already have the SD cards in them, so just flash it onto those SD cards, and you should have ROS ready to go. And then after you've done that, pick up one of the servos. The Pis come with breadboards. We've got jumper leads here, and we can start programming just ready to go. Okay. So I'll bring up the server script in just a second. In the meanwhile, I'll get you guys set up to start programming with me. Okay. Just so we are COVID safe, I will sanitize my hand and put the kits out on the table, socially distance, and you can go and pick them up. And for people online, what I was thinking of doing was, for you guys, we can go onto Tinkercad. So Tinkercad is an online simulation software where you can still run a lot of these code. So if you've done 320 or 202 in the last year, they introduced Tinkercad to you guys, where we basically pick up a platform like a TNC and we can interface with it with different hardwares. So Tinkercad already has a whole bunch of sensors that you can use, and you can try out and test programming with them. So I'll put a link for that in the chat as well. Okay, so now that you've got servos and everything working, the final step you really need is you need to put it all together. So last week we learned what Workshop 1 showed us how to do packages. So you had a subscriber and a publisher node, basically the two files. So if I bring up my repo from what we were working on last week, so let's go to that one and go to ROS Workshops. So last week we looked at this code right here, and we've got a listener node, which is our subscriber node, and then we've got a talker node, which is our publisher node, which basically will be publishing data. So this thing is acting as someone who's talking on the network, and then the other file, the listener file, is listening to what that file's talking on the network. Now, our next step for today would be to actually take these two scripts, what we learned from Workshop 1, and the script that we have for running servos, which is in Workshop 2, and combining these two together to write your own servo package. So write a simple publisher node that publishes maybe the time you want to sleep for, and then the subscriber node could be the servo script that was controlling the server, but the time coming from the publisher node. That's what we want to do. I'll do up an example and publish it on the repo for us to use after the end of this workshop, so that you guys can have an answer of how to do this.